Okay, many thanks for having me here today. I'm a distinguished software engineer at the Qt Group, namely more explicitly at Exivion. I developed clone detectors as a developer there, but my main profession is actually being a professor for software engineering at the University of Bremen in Germany. And I've done research on the subject of software clones since more than 25 years. Today I won't talk about tools. This is no kind of tool advertisement or whatsoever. I really would like to give you an insight on how you can detect clones, and in particular why you should detect clones. And I summarize the empirical evidence that was collected by colleagues of mine in the community of software clones. There are hundreds of papers on software clones alone. So we are talking about clones, duplicated code actually. The term that we use in science for this phenomenon is clone, and I prefer clones instead. You are familiar with clones. They happen naturally as these identical twins. Today we are talking about something artificial, created by humans, software namely, and also created artificially created clones to copy and paste code, or maybe through some other way. So we will first address the most fundamental question on what is a clone in the first place. This is really difficult to answer, as you will see. Then I will summarize the result on the effects and the frequency of clones, and also ways to detect them automatically. And finally, we will conclude about how to on a discussion on how you can treat them. So I would like to start with some interactive questions. Now I have two segments of code on the left-hand side, on the right-hand side. Do you think this is a clone? Is this duplicated code? Probably everybody will agree they are really copied. I mean, I did it on my PowerPoint slide. So they are cloned. That's what we call a type 1 clone in science, type 1 clone, because there are multiple types of clones actually. So now on this time, I presented a slightly different example. This time I added two comments and I changed the format slightly. As you can see here, there's this bracket here, and I moved it up one line. Would you consider that a clone? Is it a clone? Okay, yes, because comments don't care. Don't tell this to your manager. And in particular, the format is of no interest at all. So this is still a type 1 clone. Now, this time I applied another refactoring, namely a rename refactoring, substituted the sum identifier by S. Is this a clone? It's a clone, yes, but it's somewhat different. This time we have a difference. And this is called a type 2 clone. In type 2 clones, we substitute parameters. A parameter could be an identifier, but it could also be any other kind of literal, a string, a number, whatever. A single token as a parameter. That's a type 2 clone. Now this time, I add a few more statements. I introduce the calculation of a product into the existing code. And in addition to that, I also replaced this addition here by the semantically equivalent addition here. Would you consider that as a clone? So this maybe. At least the left-hand side is subsumed on the right-hand side. It's different, but it's not identical anymore. That's what we call a type 3 clone. Now, let me present you a different example here. This one here. This time I did not introduce any additional calculation. I only applied some very minor refactorings. I inlined the n assignment to n, and I turned the while loop into a for loop. Will you consider that as a clone? Yeah, probably because the argument can be made, we apply a certain set of transformation in order to transform the left-hand side on to the right-hand side, right? If this is the accepted definition, then this would be also a type 3 clone. Now, if we apply the same argument on this one here, is this a clone? Is it again? It's no clone. Well, if the argument is I apply a set of transformations on the left-hand side to turn the left-hand side into the right-hand side, then of course I can do that because I delete everything on the left-hand side and I add all the new lines on the right-hand side. Okay? Now you can boo at me, kill me, or whatever. Obviously, that doesn't make any sense, right? I mean, there should be some limit of the allowable transformation. We would still expect that the two fragments are somehow similar, beyond being written in the same programming language, of course. So there should be some limit. So it should be somehow similar. But similarity in code is a very vague term. How do we compute it? How do we decide whether something is similar enough? To begin with, how do we compute similarity in the first place? So now back again to another example here. This time I wrote this code here. Would you consider that to be a clone? Who says yes? Okay. So, who says no? Who's fallen asleep?
Well,
the argument can be made. They have a completely different syntax, obviously, but they do the same thing. They are semantically equivalent, right? So this is what we call a semantic clone. It's called also a type 4 clone in the scientific literature. It's semantically they're the same, but syntactically they're completely different semantic clones. And semantic clones are interesting too, because they're also some sort of redundancy. In essence, clones are one kind of redundancy. Now let's put this into the extreme. The argument is if it's syntactically the same and semantically the same, then it must be a clone. Is this a clone? Well, it is semantically the same. It is syntactically the same. Is it a clone? It depends. On what does it depend?
The title.
Sorry? The type. Okay, that's right. Yeah, we haven't talked about types. Maybe you have the same type. Well, probably your program will be full with these expressions. Normally, you would not consider that a clone, right? However, if you put this into a context, a different context, I can make an argument that there's still some kind of clone you might be interested in. On the left-hand side, we see two fragments. As you can see, they're completely different, except for this symbol expression here highlighted, trace.crec. Trace.crec. Now, in the version history, you can find a commit that changed those two fragments together by replacing the very same expression by the same expression on the right-hand side. So apparently there is some semantic relation between them, and then you can make an argument that they're also clones, but they're tiny. They're called microclones here. They could still be of interest. So, in summary, the notion of clones is very difficult, right? It's very complicated, more complicated than that you might think initially. Maybe you can argue this is just an academic discussion. So why should I bother? So let's look at what the practitioners have to say. You probably know the book by Fowler on refactoring. Do you? Have you read the foreword of this book? Yeah, wonderful. One person. The foreword was written by Fowler and Beck. Do you know Beck? Kent Beck? Do you know extreme programming? JUnit? Then you know Kent Beck. He's the father of both. So they wrote a foreword to this book, and they presented what they called a so-called stink parade of bad smells. And duplicate code is one kind of bad smell. And in their list, it's the topmost bad smell. Well, you can then, of course, argument it's just opinions. It's the opinions of these two pair of authors. Colleagues of mine from a Norwegian research institute asked professional developers to rank existing bad smells, and also for these, the clones were the topmost bad smells, most highly ranked. And then again, you can still say, well, now it's the opinion of many people instead of just two. It's opinions. So do they exist? That's the question. In fact, they do exist. Actually, the duplicated code clones is the most researched kind of bad smells that exist. As I mentioned, there are hundreds of papers on that. And here, some of the papers looked into the frequency of clones. And here I summarize a few of them. Those different papers differ in different aspects, foremost in the kind of projects that were analyzed. Some of them were open source, most of them actually. Some of them were proprietary, closed source software. They differ in the types of clones that were detected, also in the granularity. Some of them looked only into functions, complete functions, some of them at the line level. And then they used the different lengths, 30 len, 10, and so forth. And you see there are many, many differences. Nevertheless, all of them showed clones exist, even for type 1 clones. So all of them hint into the same direction, even though you might not even directly compare them. Actually, in one of the papers, they report a 60% of the lines of a program being copied. 60%, imagine that. It's a COBOL payroll system. We conducted the last study here in this list. We analyzed 240 million lines of open source code, 240 million lines of open source code, and found that the rate of cloned lines is actually very substantial. So I hope I convinced you they do exist. Now let me run an experiment with you. Who has ever reused code through copy and pasting? Okay. You didn't raise your hand? Yeah. Oh, yeah, sorry.
That's fiction.
Otherwise, either you are not a developer or a liar. So, why should you care? I mean, if they exist, flowers exist as well, and flowers are nice, so they're nice to have. Clones exist, they're nice, maybe it's nice to have them. Actually, they do cause harms. For instance, this is a really real example. We have two methods. They were originally identical in a Java project. They're actually they were originally the very same. And during the version history, a developer introduced this line here, but forgot to add the same line into the other instance of the clone. So this line makes sure that the null pointer dereference here does not occur. Right? So it makes sense to add it, and quite likely this should have been added there as well. So this is probably a problem, possibly. It depends on how this is called, but maybe later this program will run into a problem if this happens, that the input parameter is actually null. So there could be a relation between code clones on one hand side and defects on the other hand. And in fact, there are also, again, empirical studies. The example that I just showed you, it was taken from this example by Jürgens. They analyzed type 3 clones, clones where lines have been added, removed, or otherwise changed. And they looked in particular in this kind of clones and found that 11% of those that they inspected turned out to be defective. And that was just an example that I presented, 11%. These authors here, Lee et al., looked at type 2 clones. So type 2 clones are those where you substitute parameters. Here they looked in those in which the parameter substitution was inconsistent. But likely this could hint at an error. And in fact, they found at least 13% of those were in fact defective. Then Bettenburg and colleagues looked in 2 Java projects, and they looked into type 1 clones. These are the most harmless clones because they are identical. They're simple to find. And they looked at what happened afterwards when they were introduced, when changes were made, and whether these changes led to defects. And they found for one project about 1%, for the other project about 3%. Rather harmless, you would say. On the other hand, it's type 1 clone. But we run a similar study on more projects, more open source projects, again on type 1 clones, and we found that in effect 7% of those were changed so that defects came into existence. And we also ran a controlled experiments, 2 of my students. And then in this experiment, they had to fix clones, and quite often they found only one instance of the clone and fixed that bug and didn't find the other clone, and then did not fix it. Yeah? Yeah, afterwards they changed their states, so to speak. They were originally type 1 clones and later become type 2 or type 3 clones. Yeah. So, as I mentioned, there are empirical studies that show there's a relation to defects. The defects is one kind of harm they can cause, but other harms could exist as well, but they are not as easily measured as the number of defects. For instance, maintainability, readability, understandability, changeability, and so forth. It's more difficult to measure. Nevertheless, you can make an argument that there must be a relation, because if you have to make a change to one of the instances, you have to find all other instances of a clone. Then you may have to change them consistently, and afterwards you all have to test. You have to test all of them again. So there is an argument for that this will increase the maintainability cost. And even if you do not change the code, even if you only read the code, you have to read the same code more or less multiple times. And if it's not exactly the same and you don't know in advance, you have to make a difference somehow. And there might be a subtle differences and so forth. So you can make an argument that there are also other kinds of harms being caused by software clones. Now, if you want to find those clones, this is a very small example of a program. Nevertheless, imagine Linux kernel with 20 million lines of code, and you have to find all the clones. You won't be able. I found one example of an industrial project. They didn't find the clones that were next to each other. Next to each other, and they didn't find it. Because as soon as you have to scroll your editor, it's out of sight, basically. So we want to find clones automatically, preferably, because you cannot do this manually. So how do we do that? It all depends on how you view a program. A program, first of all, is a list of lines, and each line consists of a string characters. So it's just text. A program source code is text. And then you can apply textual searches for finding clones. So let's do that. How could we do that? Assume we want to find clones that have at least 6 lines of code. Then we could simply take each segment of code of the length of 6 lines and put it into a hash function, create a hash value, and then we slide this window here over the rest for each other until we cover the whole file or whole system whatsoever. And if you have 2 hash values, 2 segments with the same hash value, you found a clone. Right? Very simple. However, what happens if I change anything? If I change the layout, I add a comment, or do some parameterization, so this can only find type 1 clones, then it won't be find it. Moreover, if you not only want to find 6 lines, but 7 lines, 8 lines, and so forth, you have to create longer windows, and you do this comparison quite often. So it's a quite costly way to find clones. There are better approaches because source code programs is not a text. A program is a sequence of tokens. A program is a sequence of tokens. What is a token? A token is the minimal, the smallest unit of meaning for a programming language, such as a keyword, a delimiter, a bracket, and so forth. It's not just character. FOR, the string, is the for key word, right? So whatever a compiler typically runs a static analysis, the first part of a static analysis is always a lexical analysis in which the text is summarized into tokens. So we take this here as an example of 3 statements. This could be a Python program. It's quite small, but it's small enough so it fits on my slide. And then the first step would be to tokenize it. So in this step, identifiers are summarized into the same token type. So AX would be the textual occurrence of an identifier, and it would be replaced by a token ID, I in this case. And then we have this symbol, that would be a single token. Then we have another identifier that would also have the ID token. We have a plus. The number would be summarized as a number token. So we have 2 numbers here, the 0 and 1, and they would be mapped onto the same type of token. And by doing that, we abstract from the textual occurrence the image of the text of the token. That allows you to identify type 2 clones. And if you do that for the whole program is transformed into a sequence of tokens. Now, if you view a program as a sequence of tokens and you want to find clones, what you have to do conceptually is you have to find subsequences that are alike. So how can we do that efficiently? One option is we consider all the prefixes of a program. A prefix, so there's a prefix 1 that would be the complete sequence. Then prefix 2 would be the complete sequence without the first token. Sequence suffix 3 would be the complete sequence without the first 2 tokens, and so forth, until you have enumerated all the different prefixes. This is the complete enumeration of suffixes of my small example program. And now we would like to find common prefixes, because common prefixes of suffixes are clones, right? It's difficult to find that, so let's sort them. We can sort them. Then we shift them to the left, so then we can better compare them on the left-hand side. And then basically what we did was to create a data structure called suffix array. A suffix array is the enumeration of all suffixes and ordered by some lexical ordering. So I did the ordering, and this would be suffix 12, suffix 4, suffix 10, and so forth. So my program representation here would then be linear in space to the original program, which is nice. But more surprisingly is this data structure can also be generated in linear time, even though some ordering is in place. But because the suffixes depend on each other, it's more easily to sort them. Now, in order to find clones, you have to find common prefixes of those suffixes. And there's, again, a linear algorithm that enumerates all longest prefixes of those suffixes. For instance, this would report the suffix 9 and 1 as common longest prefix. And this would be then identifying this line here. So suffix 1 is this one here, and suffix 9 is this line here. And they are identical. I mean, it's type 2 clones, right? I mean, it's a small example, otherwise it would not fit on the slide, of course. But nevertheless, this is I've identified 2 type 2 clones of a single line. However, because we treat a program here as a sequence of tokens, we have no idea of the syntax. The syntax is not covered here. The problem then is then, as a consequence, we have no limit of the syntactic borders. So you could find the clones that are across syntactic borders. This is probably something you don't want to have. This is another example, 5 and 8 here. Would be also a rather small clone, of course. But this one here would be this number, this identifier, and this assignment operator. And this one here would be this number, this identifier, this assignment operator. And this is across expressions or segments, because it does not have to fulfill any syntactic constraints here. That's a disadvantage. So, what can we do better? Yes, because I lied. A program is not a sequence of tokens. A program is, of course, a tree. It's a syntax tree. And the second step a compiler does is, when it, after the lexical analysis, it applies syntax analysis in order to summarize the tokens into syntactic units. And those syntactic units are represented as a syntax tree. So what happened would be then that we summarize the tokens into a tree. The root node here would be a sequence of 3 assignments. Each assignment has a left-hand side and a right-hand side. On this particular right-hand side, we have a plus operator, which has, in turn, a left argument and a right argument, and so forth. So we summarized the things that belong together into a syntactic unit. Now, if we find clones at that level, what we have then to do is to find structurally equivalent subtrees. That's the problem we are facing here. How can you do that? One example is, again, hashing. Okay. I create a hash function. So each node of the syntax tree has a type. This one has an identifier type. This is an assignment type, and so forth. And each type is mapped onto a particular arbitrary number, preferably different numbers, of course. So I would map this onto 523 and so forth. So I'm starting with a hash for the leaves of the tree. And then I compute the hash value for inner nodes through a bottom-up hashing, which would take the hash values of the children into account, somehow mix in the hash value of the token, of the syntax tree node itself, and combine it into one and to compute another hash value. And I do that bottom up until I have hashed all the different things. Now then, I can simply identify common, similar, or actually structurally equivalent syntax tree by the same hash value. Very simple. So this is very simple. There are also extensions that allow you to find type 3 clones in syntax tree, but then this is getting more complicated. But you're getting the idea. The advantage here is, this time, every clone that is reported is by definition a syntactic unit. So this would cover the complete assignment. This would be a complete assignment. They are the same. The clones that I found earlier, which cross syntactic borders, would be excluded by construction, by design. So, but what do we do about these kinds of clones where I apply syntactic transformations? I replaced the while loop into a for loop and did some other things here. How can we find that? Here, these would have totally different or fairly different syntax tree, and you would not be able to detect it using the approach I just sketched earlier. How can we do that? Again, I lied. Sorry for that, I lied. A program is not a tree. A program is a graph, right? Why is a program a graph? Because it covers dependencies, which turn the program into a graph. And one kind of dependency is a control dependency. For instance, this condition here in the while loop controls whether the assignments in the body of the loop are executed or not. So the elements in the body are control dependent on the condition of the loop. So that's why they're nested. The blue arrows here represent the inverse control dependency. And these statements here, by definition, because they are not covered in a loop, they are at least control dependent on the entry of the foo, because foo, the function, if its foo is not executed, none of this of its assignment statements is executed. So that's one kind of dependency, control dependency. But there are also, of course, other kinds of dependency we can consider. For instance, this one here, we have an assignment here to I, which is used in the condition of the loop. This assignment also reaches in the first iteration of the loop the right-hand side of this statement here, as well as the right-hand side of this statement here. So this is another kind of dependency. It's a set use dependency. It's a data flow. You have a set to a variable, and it reaches a certain node in the tree. We have an assignment to S, which reaches this one here. If the loop is not executed at all because the condition is initially false, then this value will reach the right statement here. If you consider this one here, this assignment, if you execute the loop at least once, it will reach this statement here. It will also reach itself in the next iteration of the loop, because it also shows up on the right-hand side of the assignment. And similar for the statement of I. Now we turned the program into a graph. If you view a program as a graph, then finding clones means you look for isomorphic subgraphs. And I've applied the same process here on this one, which is syntactically very different. I get this very same graph. And this graph is called program dependency graph, because it covers all the dependencies of the program. And as you can see, they are isomorphic, so they are the same. Unfortunately, finding isomorphic subgraphs is NP complete if you have a background in computer science, so it's a very difficult problem. There are approximative heuristic-based approaches to try to find some, but they are not guaranteed to find anything. They are not sound, they won't find all of them, but they can find some of them at least. And on top of that, generating a program dependency graph is also very, very expensive, because you have to run control flow analysis and data flow analysis, which are quite expensive analyses. All right, so I hopefully convinced you that clones are real, really real, that they also may cause harms, that they are frequent, so we have to somehow treat them. The treatment could be either, one of them of course would be to ignore them, but then you fall into the trap, because sometimes, as I mentioned, there could be defects. Another way is, of course, to try to refactor them. Now, you would not go about and refactor all the clones. You would not do that, because quite likely there are simply too many. You should really focus on those that are changed frequently. So you would also have to consider the version history, as a source of information. Then you can also look in whether there was any kind of error or whether you have to write tests for those. So somehow, if they have the potential to unfold their negative impacts, then you would become active. Nevertheless, if you do not, for any reason, choose to refactor them, you have still to somehow manage them. And managing means you need to be aware of them. That means you have to find them, and it's completely hopeless to do that manually. You will not do that. You will not be able to, so you have to automate it. Then you have to also trace them across the revisions of the software, because you want to know whether they are changed, for instance. If they are changed often, quite likely you want to refactor them. And also in particular, if they are changed inconsistently, then maybe something is wrong, or maybe you have to fix them. So you might be wondering what this picture is here. Do you know the picture? Not this picture, but do you know what it means, what it shows? That's the network subsystem of the Linux kernel that we analyzed. Those blocks here are files in the Linux kernel. In this particular subsystem, the size corresponds to the number of lines of files, number of lines in the files. The color from white to red is a color gradient proportional to the degree of redundancy. The more code clones in this file, the redder. And a line connects two files exactly if they share the same clone. This one directory that I highlighted here is called IPv6. Then you see this other one with many, many edges. What do you think it's the name of this directory? IPv4. The Linux developers cloned at large, and Linus Torvald was not happy about it. So I hope you do not fall into the same trap. Thank you.